Welcome. So let's try to solve some examples on the bisection method. So as we know, to solve the bisection method, we require two values a and b, such that the function values at a and b must have the different signs. So let's calculate the function value at some random values. So I will take c is equal to 4. Put that c is equal to 4 in the given equation and calculate the value of function at c is equal to 4, and it comes out 34.190. Again I will take some other point 8, and the function value at 6 is equal to 8 is equal to 17.712. Then I will take c is equal to 12, and the function value at c is equal to 10 comes out 6.114. Again I will take c is equal to 16, put that value in the function, and the function value at that point is 2.230. So we get two values such that the function values has the opposite sign. At c is equal to 10 it has a positive, and c is equal to 16 it has a negative value, and the function is continuous between these two values. So by intermediate value theorem, the real root must lies between these two values. So by first approximation, by bisection method, first approximation of root by bisection method, let's take a is equal to 12 and b is equal to 16. I have taken these two values as a is equal to 10, 12, and b is equal to 16. So first approximation of the root is just average of these two values, equal to 28 by 2 is equal to 14. So then check the function value at this new root, and it comes out to be function value 1.611. So at x1 the function value is greater than 0. Therefore second approximation of the root, second approximation is x2 is equal to, now we have to replace, since x1 is greater than 0 and at f of, let's write here, f of a is equal to, means f of 12 is equal to 6.114, and f of b is equal to minus 2.230. So at the new root the function value is positive, so we have to, by taking the second approximation, we have to take the value between a and b such that the function value is the negative. So at x is equal, at b the function value is negative, so second approximation will be b plus x1 divided by 2, and which is equal to, b is equal to 16, x1 is equal to 14 divided by 2 is equal to 15. Again check the function value, add new root above 15, and it comes out 0.384, and which is less than 0. So for the third approximation, the x2 value, at x2 the function value is negative, so we have to take the value between b and x such that the function value should be positive, and the function value at the point x1 is positive. So third approximation will be x1 is equal to x1 plus x2 divided by 2, and which is equal to x1 is equal to 14 plus 15 x2 by 2 is equal to 14.5, and continues this process until the new root this reduces some threshold value. So you have given some threshold value, epsilon a is equal to 10 raised to minus 3 or something. So calculate, so continues this process until this condition is reached. So check at each step, calculate this value. At this stage calculate means we get x1 is equal to 14, so 14 minus, so x is equal to 14 minus this b value 16 divided by 14 is equal to something, then calculate here the new root is equal to 15 minus older root is 14 divided by 15, calculate this value. This value comes around approximately 1.3%, and this value comes 5.3%. So then this calculate this value 14.5 minus 14 divided by 14.5, and if it is not less than given threshold, then continues the same process until and unless you reach that threshold. Once you reach that threshold, stop the iteration, and that is your best approximation for the root given by the bisection method. So now let's move some more details into the bisection method. So the actual error means true error in the bisection or any method, true error, true relative error is equal to actual root minus approximated root divided by actual root. This is the true error, but while calculating the error in this example, we take the new root value and the old root value, because if we knew the true root value, then what is the point of the numerical methods? If we know the true root value, then there is no point to calculate the root by using the bisection method. So there is another procedure to calculate the error, and which is approximate relative error, and this is calculated by new root, that is xr new minus xr old divided by xr new into 100. This is the percentage approximate relative error, percentage relative true relative error. So these are the two relative different types of relative error. Third is the absolute error, and absolute error is only difference between the xr new minus x old. This is the absolute error in the error in numerical method. So it in bisection method, it is there is very important result. So we can calculate the number of steps required to decide the absolute error. Means if we have given some desired error, suppose it is given 0.0625. Suppose we have to uh, calculate the what is the number of steps required to reach or to below that error. So in bisection method we can calculate the number of steps. So it is very simple. Suppose at first iteration the error is delta x naught, and which is the difference between the b minus a. Okay, then second iteration we take the means suppose this is a and b. So after first approximation is calculated average, so this is x1, so error becomes half. Okay, so it becomes delta x naught divided by half. Then again either of the if this value is negative, then either of the value is positive, then again we will take average, so again it will become half. So delta x naught by, so after nth step, similarly after nth step what we can write about the absolute error is equal to delta x naught divided by 2 raised to n. So after nth step we can get this much of the error in bisection method. So we have given the desired error here, and now we want to calculate the how many steps required to get this desired error. So we arrange the equation 2 raised to n is equal to delta x naught divided by e b raised to n. Apply log on the both side, we will get log of delta x naught divided by ab raised to n divided by 2. Then we know delta x naught, which is in first example, delta x naught means initial values that we have taken as a and b. That difference between that two values is delta x naught. So it is 4 divided by, we want this error at nth step, so 0.0625 divided by 2, and if you calculate it approximately comes or equal to 6. So after sixth step we can get the desired error, or we can reduce the error below that error in bisection method. And this is the advantage of the bisection method. We can calculate the number of steps required to reduce the desired error, means number of steps required to reach the desired error. Okay, now after seeing the bisection method, let's see the regular falsi method. So it is same as the, means, so initialization is same as the bisection method. We require the values of c such that the function value has the opposite signs, and as we have seen in this example, that at the 12 and 16 we have the we get the function with the different sign value, so we will continue with that only. So first value a is equal to 12 and f of a is equal to 6.114, value of b is equal to 16 and f of b is equal to minus 2.230. So by regular falsi method, we know the formula of the regular falsi method. X1 is equal to a f of b minus b f of a upon b minus a. Put the values b f of b minus 2.230 minus b 16 into f of a 6.114 and divided by b minus a 16.12, and solve these and we will get x1 as 14.309, x1 as 14.309. Okay, now calculate the function value at f of x1. So f of x1 14.309 and it comes out to be minus 0.2515. Okay, now this value is less than 0. So for the second approximation, we is equal to 12 because it has positive value 6.114, but b is equal to, we have to assign this value because we need the function value which has the opposite sign, and f of b is equal to minus 0.2515. Again, sorry, again calculate x2 is equal to a f of b minus b f of a upon b minus a. So a is equal to 12. Now f of b is equal to minus 0.2515 minus b is equal to 13.039 and f of a is equal to 6.114 divided by b minus a, b 3.09 minus a 12. Calculate this value. Let's calculate what it comes. Okay, so 12 into minus -0.2515 minus 14.309 into 6.114, 14.309 minus 12, and it comes out to be it comes around 14.142. So again check the value at f of x2. If it is negative, check whether it is the negative less than 0 or greater than 0, and according to that assign the values to the a and b. Calculate f of a, f of b, and again use the formula for the next approximation of the root. And as we seen in the last example, stop the iteration when that approximate error reduced to some given threshold. Stop the method, and this is your best approximation for the root. So okay, that's it for the bisection method and the false position method. I have given the overview of the two methods, and the next video we will see some examples on the numerical Newton-Raphson method and the secant method. Thank you.